state vector of the components. Sorry. So the deep neural network will take the state vector of the component into the input layer and output the Q values for each possible repair actions. Then each time step, the agent will take the repair actions with the highest Q values to add on the environment. And the reward function is defined as the system functionality improvement over its repair time. So a higher reward means a higher recovery efficiency. And finally, we will use some Q-value-based algorithm to update the network parameters by minimizing this Bellman's equation in this task. Then we apply this framework to optimize the post-earthquake recovery of a practical substation system. As a first task, we extract the system into nodes and edges in a graph structure to capture the topology and also interdependency between the components. And we define the system functionality as the transmission capacity to consider the redundancy and also some electrical constraints in the system. Then based on this system model, we can actually simulate the post-earthquake recovery of the system after the earthquake, so that we can generate many experience composed of the state action reward and next state. And this data set will be fed into these reinforcement learning algorithms to learn the best repair policy that can maximize the resilience goal. And in our study, particularly, we compare 4 reinforcement learning architectures. And we found that double DQN can perform best during the training. So this model will be directly applied for future application. And we first test on some random damage scenarios with different damage levels, as shown here with 8 damage components, 16, 32, and 40 damage components. And our model can always determine which component to be repaired next based on the current component states, so that we can generate this recovery trajectory based on this model. And we further compare the results with those from the traditional genetic algorithms, as shown in this figure, and also listed in the table. We compare in terms of the resilience matrix and also the computational cost. And as shown in these tables, our model can always achieve the better optimization effects and also achieve higher efficiency. So a small summary here is that this work proposes a cost-effective structural seismic health monitoring scheme for the interconnected assets. So by just monitoring the ground motion signals, we can provide a real-time assessment results for the interconnected assets based on the physics-enhanced graph neural network model. And this information can be further input to the deep reinforcement learning-based optimization model to inform emergency repair actions to enhance the system resilience. So from end-to-end strategy for this substation system health monitoring. Okay, this slide also discloses my presentation today if you have any questions about this.
Thank you very much. Do we have any questions either online or here?
Maybe I can make the connection a bit to what Huangbin showed and some of the work that is going on in the group, as well as those visiting us. So in the first part of his presentation, Huangbin showed how reduced order models can be used for seismic assessment of interconnected assets. He touched on assets that are particularly exposed to earthquake or seismicity effects, which ties to Livia's interests. So I would encourage you to exchange with Huangbin. Of course, he uses graph neural networks and reduced order modeling in the loop, which touches on work that Marcus and Greg also have been trying out with mass spring systems. In that case, here it's about the real finite element models that are being reduced. I think Greg has a question, so I'll give him the floor next. And the last connection I want to make is on decision support on the Q-learning framework, which is essentially a reinforcement learning approach for deciding what are the best repair actions in a system of interconnected assets. And this is tied, obviously, to the work of Giacomo, but maybe also of interest to Livia. So please recognize these connections and get in touch, because it would be tremendously beneficial, given that, of course, Huangbin is situated a bit far, but is reachable, of course, through our Slack channel. The Singapore group is a member of our group. All of the members are members of our group, and you can reach out to them at any time. So that's just the input from me.
Yes, thank you. Thank you, Ellen.
I guess, Greg, you can go ahead with your question.
Great, thanks. Can you guys hear me? Yeah. Thanks, Huangbin, for the very nice presentation. I have two questions. The first one was, I mean, you had showed me before this work that you were doing with the GNNs for your problem there. Is there, at some point you had tried to put the ROM back into the aggregation scheme? Yeah. Remember, I don't know if you remember, we discussed about how you could potentially do it in an iterative way. Did you try this ever?
No. At this time, I still do it in one message passing, just doing one step. I do not do it iteratively.
Okay.
Because this is also a bottleneck for the reduced order model. Because for the reduced order model, I also need the previous time step system state, which is not a hidden representation of the null features. So I cannot think of a way to do it iteratively.
Okay. I mean, we can discuss this again offline if you are interested in trying. I think you need to remind me again exactly how it works, but I think we had a pretty good idea. Yeah, I was just wondering if you had tried it or not.
Nice. Oh, I think we can continue the discussion after this.
And also,
maybe
the other
I can
question
mention, because I've also exchanged on this with Huangbin. I think what he thinks is a bottleneck is that he needs the previous state.
Yeah.
And that's why he tries to do it in one step. But I think you can also do it iteratively. This wouldn't, probably you would have some sort of convergence. His fear is that because you're enforcing, f is equal to kx, essentially, right? His fear is that enforcing it in iterations may actually not reflect the full equation, but that shouldn't be a problem, because that's how we solve that equation in approximative solutions for finite elements. Actually, we iterate on f is equal to kx. I think it's doable.
Yeah, because I remember we had this discussion, and I thought maybe if you were to do it iteratively, I don't think you would need that many steps, as actually solving it.
It would be great if you can discuss. I agree with you, Greg. Yeah.
The other question was about the RL framework that you're doing. It's very interesting for Giacomo and I, because we started, incorporating graphs and topology-aware agents now in the work on the railway systems. Did you try training on? So, when you were solving your environments, do you do it only for one given topology, or do you do it for many and then test on one, or I don't know, or train on one topology and test on many? I don't know. Can you tell me a bit more about how you do that?
I'm not sure if I understand your question clearly. So for the environment here, I use the graph-based representation to build a system model. And so based on this system model, I can generate many data sets for the reinforcement learning algorithm for its trainings. So the graph-based representation is just used for generate its data set for the reinforcement learning algorithm. So I do not use the incorporate the graph neural network with the reinforcement learning algorithm, because I can see there are some work in the literature. They just embedded the graph neural network to the reinforcement learning. So at the beginning, they just use the graph neural network to abstract the feature from the graph. And then they input these hidden features into the reinforcement learning for its learning, the best policy to do it. So it's different. I'm also thinking of in the future, because for the power systems, it's very useful to use a graph-based representation. And then if we can combine the graph neural network with the reinforcement learning, I think it's a very promising direction to do it.
Yeah, I think it's really cool. We're doing this with Giacomo, where we're using a okay, we're already doing kind of the same with a graph-based representation for the environment, but then we're also using topology-aware agents, so like GNN or transformer in the agent itself. And what's interesting about this is you can train, so we're also doing multi-agent RL, but you can train your agents on a much smaller environment and then apply them to a much larger one, and it still works. So I was wondering if you had thought about doing something like this for this.
Great. So you mean you first train on a small scale system and then you do the transfer learning to extend to a large scale network?
Not even need to do transfer learning because the agent has learned to solve this graph-based environment. So you can directly apply it to a larger one. It becomes interesting because, you know, for like solving multi-agent systems, it's really expensive to do it on when you have a lot of nodes. But if you have, if you can train on a much smaller environment and then apply it to a much larger one, it becomes super interesting. But we can, if you're interested in this, we can get in touch as well with
sure. Sure.
Okay, do we have any more questions for Huangbin? If not, maybe we can move on to the next presentation, again from the FRS group, right?
Yes, it will be me.
Okay, great.
Can you see my screen now?
Yes, looks good.
Okay, I'll start. So today I'm going to present actually the project here at FRS, which is Dynamic Mobile Sensing Platforms, and I'm going to present our field study of the robotic mobile sensing platform for a population-based structural health monitoring. And this work is conducted by Kiran and our research intern Shixing and me. So first, I would briefly introduce the background. So as we know, structural health monitoring of civil engineering structures has become a very hot topic, research topic in recent decades. But if we look at the practice, like engineering applications of SHM on civil engineering structures, usually we only focus on like very large scale structures like those like cable stayed bridges. But actually, in our civil engineering infrastructure, most of them they are short and span medium bridges, for example, and they have a large amount, but so far we don't have a very effective like inspection tool or monitoring tool to conduct SHM on them. So there is still some gap between the application and the research efforts. And in order to implement SHM on this massive infrastructure network, of course, we need to change our sensing method because the traditional structural health monitoring paradigm, which basically are based on the fixed sensing scheme, it deploys fixed sensors on the structures, and this is although this is already tested and mature for many individual structures, but if you want to scale it up to apply this on many structures, this is infeasible because it's very labor intensive and cost time consuming to deploy those sensors on many structures. And in order to solve this problem, so in our project, we propose that we put the sensor on a mobile platform. So this platform can be a train, which is what Hara is doing now in Zurich. And also it can be a robot or a bicycle, and that is our project in Singapore. So if now we only focuses on the using robotic mobile sensing platform for the inspection of bridge structures. This is because at first we try to use a vehicle like a car to do this, but it's very difficult because when a car moves on the bridge, actually the vibration of the car is mainly caused by the road roughness, and the road roughness is not what we want. So that's why we choose the robot to conduct this mobile sensing, because if we use a robot, we can like control the robot to make it stop and go on the bridge. So when the robot robot like stay static on the bridge, we measure the vibration of the bridge. So in this case, we don't have any interference or noises caused by the road roughness. And in order to test this robotic mobile sensing approach, first we conducted some theoretic and numerical studies, but I'm not going to talk about details of those because this has been published in our previous paper. So today I will mainly introduce our recent field study of this approach. So in terms of field study, first I would like to introduce our hardware. So the most important one is our robotic mobile sensing platform. As you can see here, first we purchased a robotic platform, which is shown here at the bottom, from a company. So this is already a commercial product, and it's off the rack and it's cheap. Just compared with cars, it's just like $1,000 for this robot. And based on this robotic platform, we made our own modifications. We installed like a high-end accelerometer and satellite sensor on top. We also have a GPS antenna, like infrared distance sensor to avoid for example, to avoid the robot collide with the obstacles. We also have cameras, which allows us to use some computer vision techniques to navigate the robot and so on. And beside the robot, we also developed our own acceleration sensor. And this acceleration sensor is currently used as a reference sensor deployed on the bridge, because we know if we want to identify, for example, the mole shape of a bridge, we at least need 2 sensors. And you can see this customized accelerometer consists of accelerometer module here and a GPS module, GNSS module here to receive satellite timestamps and position coordinates. And we have a processor, which is a Raspberry Pi, to process those data. And after these two, one mobile sensor, one fixed sensor are ready, we tested them on a population of bridges in Singapore. And this is our collaboration with the Singapore Land Transportation Authority, which is the owner of all the bridges in Singapore, actually. So why we choose this bridge for test? Because although this bridge, which is called the University Flyover, is only one bridge, but actually it consists of, in total, 15 simply supported bridge spans. And we conducted our test on 12 bridge spans among the 15 spans. And they are simply supported. So they are they are actually, we can take them as individual bridges, because it's simply supported bridges, they are kind of independent from each other. And although they are similar, but they are different. Like, for example, you can see there are some longer spans, there are some shorter spans. Some spans, they have 4 vehicle lanes, traffic lanes, some only they have 3. So they have also some kind of diversity. And here you can see these are the close photos of those bridges. You can see they are simply supported, like here they're divided. And this is a test up of our study. First, because we customized our own sensors, so we can write our own programs to control those sensors. And it's very easy. On the bridge, we can simply use a laptop or even a smartphone to send our commands to the sensors to start data collection or end data collection. And this is the first thing. And second, we conducted the mobile sensing using the robotic mobile sensing platform in a stop and go manner. I have mentioned this previously. So for each stop, the robot stays on the bridge for about four minutes, and we only use this data for bridge structural model identification. So when the robot is moving, we don't use those data because those data are polluted by the road roughness. And finally, we also deploy the reference sensor, the fixed sensor on the bridge, like a quarter span. This is used for the mole shape identification. And those sensors, although they do not communicate with each other, but they are synchronized. And this is very important for structural health monitoring. And this synchronization is done by synchronizing these time steps obtained from the satellite clocks. and the sampling frequency is 100 Hertz. So after we finished the setup, we collected a lot of data, and the first thing we did is to do data pre-processing, because, for example, you can see here in the time history acceleration signals, there are some like perturbations caused by, for example, when a pedestrian passed by, he accidentally touched our sensors, so there will be some noises, and we need to remove this. Otherwise, you can see the signal is not useful. And here we use a Hampel filter to remove these outliers. After the removal, now the signal becomes normal. And based on, after this, we developed a robust model identification framework to analyze those mobile sensing signals. Why? Because we are using a mobile sensing approach to connect data, and you can imagine for mobile sensing, its uncertainty is higher than the traditional fixed sensing, because first our sensing position is changing, and second, like the sensor, the accelerometer is now deployed on top of a robot. It's not directly deployed on the bridge. So the mechanical property of the robot will also influence the vibration, and this introduces more uncertainties. And the last reason why is because now we are using mobile sensing. We do not apply any like controlled excitation on the bridge. The bridge are purely excited by random traffic flows. So this also causes more uncertainties. And in order to deal with those uncertainties, we developed this robust model identification framework. So the first step we did is to window the original signals. We are using a sliding window to divide the original signals into many small segments. And for each segment, we apply the automated frequency domain decomposition method on them, because this is a modification algorithm that is very suitable to process short-term measurements. And after this, we can get natural frequencies and mode shapes. Here, we don't identify damping ratios because the vibration signals we connected are significantly influenced by the vibration of the robot as well. So the robot has its own damping characteristics. So consider this, the damping identification using mobile sensor will be very difficult. So we just give up. Anyway, based on the natural frequencies and mode shapes, now we perform some k-means clustering. Based on the clustering result, we can get very many frequency clusters, and for each cluster, we have many measurements from those signal windows, and then we can perform uncertainty evaluation on this. And based on the k-means clustering results, we can also get many clusters about identified mode shapes. And then we can also perform uncertainty evaluation. And finally, we can introduce the satellite positioning coordinates to get the position of those identified mode shapes. And finally, based on the uncertainty evaluation, we can evaluate the reliability of those identified modes, and we can just pick out those reliable modes and as the final model identification results. So let me illustrate how we use this approach. For example, this is frequency identification results of the data we connected on the East 3 span. So first, you can see here there are many points on the left. So each point represents the frequency identification results from one pair of signal windows. And you can see for some, and this is already the clustered result. So you can see here, this is definitely a stable mode because we can see many points, their distribution are quite close to this central line. And also, for example, this one, this is also a very stable mode because it's more concentrated near the center. But for the higher modes, you can see that those points are more scattered, indicating there is higher uncertainty. So this is results of frequency clustering. And based on the frequency clustering, now we introduce the satellite positioning results. which I show here. So you can see this is the inspection trajectory of our robot on the bridge, and the accuracy is very high because we just made our robot move on the pedestrian sidewalk of this bridge. So, and in total we measured 12 spans, but here we only compare the results of these 10 spans because we have stop and go test on those 10 spans. And this is mode shape identification results of the span E3. So you can see here, on each point, because we conducted frequency clustering, so on each spot, on each stop, we also have many measurement points of those mode shapes. And if those like crosses are more concentrated near the center, this indicates the uncertainty is lower. If the crosses are more scattered, this indicates the uncertainty is higher. So based on this, we can also see which mode shapes are more reliable, which mode shapes are less reliable. For example, this is definitely more reliable than the mode 1 is definitely more reliable than the mode 4, because you can see mode 4, like those crosses are very scattered. And also we can see like for higher modes, their uncertainties are higher. For example, for the mode 6, you can see the crosses are much more scattered than like mode 1. But anyway, the identification results looks nice because we know for simply supported bridges, their first mode shape should look like a half of a sinusoid wave, and for example, their higher mode shape should look like a full sinusoid wave, and their even higher mode shape should look like a 1.5 sinusoid waves, and these are all reflected in our identification results. And those observations also apply to the other bridge spans. For example, this is a span west 3. So you can see some similar frequency clusters, also similar frequency mode shape identification results here. And also we created some finite element models to verify whether our model identification results are correct. So because we don't have like very accurate designing parameters of those bridges, we can only roughly estimate those parameters. So I built this finite element model based on a general setting. It's like 35 meters long, 15 meters wide, and I use solid element to create those FEMs. And you can see, for example, these are the mode shapes and frequencies of the FEM. You can see for the first mode shapes, they just look like a half of sinusoidal waves. And as you see previously, this also from our identification results, this is also the case. And for their higher mode shapes, it looks like a full sinusoidal wave. And also we successfully identified these mode shapes in our experiments. So the FEM analysis successfully verified our field test results. And furthermore, we conducted population-based analysis on those data. For example, first we can look at these population-based observations on modal frequencies. For example, first we can clearly see, like for bridge span east 125 and west 125, because they are in pairs. Like you can see here, we have east 1 and then we have west 1, and their structure type is the same, basically the same, and their length is the same. So they should have similar frequencies, and this is also reflected in our identification results. So you can see there are two groups of frequencies in the bar plots. This is the first group, this is the second group, which indicates the bridge that are in pairs. They have almost identical frequencies. And furthermore, we can see like for longer bridges like span 3 and 4, either east or west, they all have lower frequencies than others because they are longer, so their stiffness is relatively lower. So they should have lower frequencies. So this is also consistent with our engineering knowledge. And third, even for some subtle differences, we can observe from our identification results. For example, you can see here the bridge span east one has a higher frequency than west one. This is also reasonable because you can see here the west one, bridge span west one, it has 5 traffic lanes, but for east span one, it only has 4 traffic lanes. So ideally, theoretically, the stiffness of west one should be lower than east one, and its frequency should be lower. And we also get some observations on the mode shapes. For example, you can see here, I show the first of 3 identified mode shapes of all the span on the west here. You can see, for reference, I also show the like half sinusoidal wave here. So you can see for most identified mode shapes, their Mach value between the identified mode shape and the half sinusoidal wave is above 0.9. So this indicates the identification accuracy is good. And you can also see, for example, for those identified mode shapes near the bridge support, like at the 2 ends, they have higher uncertainties because this is error bar. So if the error bar is larger, indicating the standard deviation is higher. So for measurements near the bridge supports, it has a higher uncertainty. This is also reasonable because the vibration near the bridge supports is weaker. So for weaker measurements, its signal to noise ratio is lower. So definitely should have higher uncertainties. And for some measurement points not very near from the support, it also has high uncertainties. This is because for those measurement points, like a pedestrian passed by, they accidentally touched our sensor, so this caused some perturbations. And this can also explain why high uncertainties occur here. So in summary, in Singapore, in our research group, we developed a robotic mobile sensing approach. And it consists of both hardware solution, like algorithm solutions, and the entire solution is validated by field tests. And we also proposed a statistic framework to robustly identify model frequencies and mode shapes. And those identification results, they are not only verified by finite element model analysis, they are also consistent with our engineering knowledge about bridge structures. So indicating the identification results are good. And in the future, we will do more study because this is a very valuable data set, consists of a population of bridges. I've never seen this kind of data set before. So furthermore, based on this data set, we can conduct more study on the population-based structural health monitoring. So this concludes my presentation, and I look forward to your questions. Thank you.
Thank you, Xudong. Do we have any questions for Xudong?
Hi, Xudong. Can you hear me?
Yeah, I can hear you.
Yeah, I have a clarification question. So I want to know, does you only use data when the robot is stopped, or you also considering the data when it is moving?
I only use the data when the robot is static. Because if the robot is moving, like its vibration is mainly caused by the road roughness, and usually this vibration caused by the road roughness is based on our previous experience, it's 100 times stronger than the vibration caused by bridge vibration. That's not what we want. And this is the reason why we are using the robot, because if you use a car, you cannot flexibly stop and go. But if you use a robot, this is doable, and we can write a program to control the robot to make it automatically stop and go on the bridge.
Okay, so all the data you use for the identification is when it is stopped, right?
Is what? Sorry.
So you use data when the robot is stopped on a certain position, and then you use the data to identify the frequency and the motion, right?
Yes, exactly. You're right.
Okay, thank you.
Thank you.
I also wanted to ask a question, Xudong. Like when you do after the automated FDD, that you do the clustering of the mode shapes and frequencies, how sensitive is the clustering to the clustering parameters that you are using for the k-means?
I think it's not very sensitive because, for k-means, basically the only parameter you need to set is the number of clusters.
Okay.
So here you can see the number of clusters I use is 12. But if you set it as 9, it doesn't change much. But of course, you cannot use like 4 or 3, then the results are not acceptable.
Yeah, what I mean is if you go like very high, it's not that it's gonna like, start cluster, because I have seen sometimes, okay, maybe my data is not as clear also, depending like on the numbers of clusters, sometimes, the clustering changes, and then that's why I wanted to ask.
Yeah, and yeah, one thing to add, and you can see there is a trade-off of the number of clusters you set. If you set it very low, then of course you cannot identify some mode shapes or modes. But if you set the number very high, and then through here you can actually do some based on the identification results, you can remove some fake modes. For example, here you can see there is a like a blank in the middle, which means for this cluster it doesn't have sufficient points. If it doesn't have sufficient points, this means this cluster is not useful. So even if you set a very high number of clusters, like you can still get rid of some meaningless clusters by checking the identification results.
Okay, you just do it manually, like based on engineering judgment, let's say.
Yeah, you can do this manually, and you can also set some threshold to evaluate those identified mode shapes or frequencies. To evaluate its uncertainty, for example, if its uncertainty is too high, then you don't need to use it. You cannot trust the identified modes.
Okay. Thank you, Xudong. Do we
Yeah,
have
thank
any?
you for your question.
Maybe
Can you
yeah,
hear
go
me?
ahead.
Yes, Vasilis.
Hi, Xudong. I would like just to ask if you have a cost estimate of your robotic vehicle. Rough.
Sorry,
Cost estimation.
cost estimation. I
Yes.
think in total, all the hardware we have, we cost about $2,000, right?
Okay.
Including the robot.
Including the robotic vehicle and all the sensorics.
$2,000 for all the, including
Yes,
the.
correct.
Okay. Nice.
And maybe a small comment from my side again to link the work. Obviously, it has to do with mobile sensing and the work Hara does. So the team is in touch with Hara. But Xudong has also specifically been developing quite efficient operational model analysis tools based on the frequency domain decomposition method. Xudong, I would like to ask you, recently you forwarded a file that does, a script that does processing. I was wondering if you would like to upload it in your GitHub, and maybe we can make it available for the research community. You should then upload it on some simulated data, perhaps, so that it's not proprietary, or maybe the data from this bridge, because we can use it, I think. We don't need permission.
Yeah, this is a very nice suggestion. And currently, I'm preparing a research journal paper about this research. And I thought after I finish the paper, I will upload the algorithm.
And I think it would be a very nice tool of general purpose, which is operational
Yeah.
modeling. Okay, great.
Thank you.
Okay, if we don't have any more questions for Xudong, then maybe we can move to the next presentation so that we can make it in time. You are also presenting, Kiran?
Sure. Yeah. I will try to make my presentation quick.
Okay, good. Thanks, Kiran. Then the floor is yours.
Sure. Okay, good morning, everyone. Today I'll try to talk about the work that I did in the latter part of my PhD, which focused on spectrally biased physics-encoded neural networks. Let's just jump into it. Basically, when it comes to SHM data, we know that when we try to measure structures based on vibrational data, the data can be quite dense. But if we project the data into the Fourier domain, suddenly it becomes the information is concentrated on a very sparse number of frequencies. And therefore, like techniques such as the FDE are often used to analyze structures and to guess their geometry based on the spectrum. On the other hand, because of new mobile sensing techniques that Xudong just mentioned, we can accumulate much larger data sets than what were previously possible. And because of this, machine learning methods are becoming more and more important in the field of SHM. And but we know that the information is concentrated on the spectrum. So how do we sort of marry both of these ideas? How can we like benefit from the data-driven approach of machine learning, which can process huge amounts of data, and also this prior knowledge that we have on the sparsity of the spectrum for SHM data? So of course, there's a plethora of models, but essentially here we will focus on what we call physics-encoded neural networks, where we try to encode the prior information in the architecture. More so, we choose the right architecture for the right problem. And here we want to see if we can choose the right architecture based on spectral sparsity, so the bias of spectral sparsity in the data. So for our work, essentially, we start from the observation that FIR filters, AR models, and CNNs, they all share the same structure. Namely, they all perform a convolution operation. In the case of finite impulse response filters, we just want to have a causal filter to target a specific bandwidth. Whereas an autoregressive model, we're just trying to make future predictions based on past time steps taking into account noise. And then if we have a cascade of such models, then we obtain essentially a linear convolutional neural network. So a convolution that's done multiple times across multiple layers. Now, convolutional neural networks have enjoyed wide success mainly in image processing. So essentially you convolve in 2D, and then based on the feature maps that are obtained, you try to use these features to tackle different tasks. However, it's kind of a known fact that images, if you take the spatial frequencies, they have a huge low frequency bias, and the frequency actually follows a power law. So because of this, most of the CNNs that were developed maybe unconsciously with this low frequency bias in mind. However, we know that for SHM data, we want to target not specifically the lower frequency, but actually like sparse peaks in the spectrum. And in this case, the CNNs used in the literature that have short kernels are not adapted to target specific frequencies. If we look at the bandwidths for FIR filters, we can see that if we only use five taps, which is quite common in the literature, it's impossible to actually obtain a specific bandwidth. And so we opt for using much longer bandwidths than what have been used before. So we use sort of signal processing intuition to justify our choice of architecture. Interestingly, there's actually a completely different field that focuses on the implicit biases in neural networks. So actually, this is a field of mathematics where they try to prove mathematically that neural networks have specific biases in them, essentially that they have an implicit regularization of their weights. And there's a paper that demonstrated that CNNs actually behave like diagonal networks in the Fourier domain. So diagonal networks are these kind of toy networks that you see in the middle. So instead of having this all neurons being interconnected, it's a one-to-one connection. And so the CNNs, and so the other papers have proven that these networks have a sparse bias on their weights in the spatial domain, which means that the CNN will have a sparse bias in the frequency domain. However, they make a lot of different caveats to demonstrate this. Namely, the CNN has to be, the length of the kernel has to be as long as the input signal, which is unfeasible for real data. In our case, we just say that they're much longer than usual, but sort of a compromise between the length of the signal and the computation that we have at our disposition. So we first come up with this just a simulated experiment. So we want to see if the CNNs actually do have this sparse bias implicitly. So what we do is that we generate spectrally sparse data, and then we train the CNN to map white noise to this data. And once we've trained the CNN, we extract the weights, convolve them together to obtain a single filter. And then on the same data set, we obtain a least square optimal filter for the specific bandwidth. And then we compare it with the filter that we obtained from the CNN. And of course, you can already see the results, like the spectral responses and the filters themselves actually superpose each other. And we verified this for different peaks in the frequency band because, it will yield filters with different sort of oscillations. And so we can verify that in each case, the CNN actually converges to the same configuration as the least square efficient filters. So this was just to confirm our intuition. So now we try to apply this knowledge for SHM tasks such as system identification. So here, this is again still a toy example. We have a beam on which we excite with white noise, and then we use the white noise excitation as the input, and we use the acceleration time histories as the output that we try to predict, and we train our CNN to learn this mapping. So here we can see that even for and once trained, we extract the filters and we plot their impulse responses. So this is not the outputs of the, here we don't have the spectrum of the data, we have the spectrum of the filter, which is important to note. And so we can see that the frequencies have actually been encoded inside the filters of the CNN. And more interestingly, we can do this in an unsupervised fashion because usually we don't have the response of the system. We don't have the excitation of the system, sorry. So what we do is that we take the acceleration time histories, we use the LSTM to try to extract white features from the data. Then from these white features, we actually map them back to the original data. And then we look at the impulse responses of the different filters that are learned. And we can see that most of the modes, or at least the lower modes, are recovered by our filters. Of course, we tried this method on real data. So here, maybe some of you have heard of the Z24 benchmark dataset. So this is a bridge that was destroyed in Switzerland in the 1990s. And before destroying it, they performed a whole bunch of ambient and forced excitation experiments and recorded the vibration across the bridge, across the entire bridge. So we just take the data from this bridge and we perform the previous experiment. And we can see that when we look at the filters, we can see that the filters sort of specialize on different modes. And what's interesting is that many filters actually specialize on single mode. So they were able to perform they're starting to perform a form of single mode decomposition. Although, of course, you can see that many other filters are not able to recover a single mode, or some of the modes are actually completely ignored. And then, of course, we can compare with the FDD to see like what are the frequencies recovered by the FDD, and we can see that they sort of align each other. Of course, our method doesn't replace FDD. Like from a computational perspective, training a neural network is much more intensive than just performing a fast Fourier transform. But it's more so to show that the complex operations that are performed inside a neural network, if you try to break them down and try to interpret them, you can find similarities with traditional methods that are used in SHM. Now, one more thing. So I just mentioned that there was a semblance of single mode decomposition. So I tried to force this decomposition by adding a pre-filtering layer. So we know that short kernels can become low and high pass filters. So we add a few filters in the beginning that are short kernels, and we hope that they will specialize different bandwidths for different filters that have long kernels. And so again, we train like a simulated beam. So here I chose 6 degrees of freedom because it's kind of high enough for it to be tedious to calculate for humans, but it's still easier to visualize. So adding this pre-filtering, we can plot the different impulse responses for the different filters. So we can see that without pre-filtering, there's a huge overlap. Whereas when we add the pre-filtering, we're sort of able to distinguish the different frequency modes. And then once we've done this, actually, since the last operation that is performed is a linear projection after the filters, which now specialized on single modes, actually this projection is simply the columns are simply the mode shapes of our system. So we just look at the mode shapes, we normalize them, and then we compare them to the true modes of the system. So here I've highlighted in the same color similar modes, and you can see that most of the low mode shapes have been recovered, actually even the higher ones, but subject to some uncertainty, of course. But essentially we can start performing a form of mode shape identification with this method. So yeah, this is the work that we performed on CNNs. However, one thing I figured out was that the problem is that if you use longer and longer kernels to target specific bandwidths, if you think about it in terms of computation complexity, actually the computation scales with the square of the length of the kernel. And actually, no, it's linearly with the length of the filter, but square with the number of channels you need. And actually, this is much less efficient than just performing a Fourier transform. So actually, there are other types of neural networks that perform a Fourier transform and do the computation in the Fourier domain. And they're actually much more efficient than our method. So in terms of like practical application, we have a huge disadvantage in terms of computational efficiency. However, this project actually helped me sort of dive into the implicit biases in different neural networks. So we saw the ones for CNNs, but then there's actually these diagonal neural networks where we know that by default, they will always converge towards a sparse configuration, which means that once they've converged, they operate as a sparse selector on the data. So before I mentioned these methods that perform a Fourier transform and then use the neural network in the Fourier domain. So what if we combine these two ideas? We use the computation in the Fourier domain, but instead of recovering a dense Fourier inverse transform, we use this sparse selector in the middle to sparsify our frequencies before performing the inverse Fourier transform. So of course, here I'm switching gears completely because I want to do a one-to-one comparison with the original paper. So we're not talking about structures anymore. Here we're dealing with solving PDEs. So the first problem they solve is to essentially find a forward predictor for the Burgers equation. So in this case, we just train the model with and without sparsity. So the model that is trained with sparsity, we can find the sparse coefficients of the sparse selector, and then we can compare it with the modes that are truncated in the original method. So here you can see that the frequency, the x-axis is logarithmic scale. So actually they truncate a lot of modes, but even with this large truncation of modes, we were able to find an even more sparse representation. So we actually truncated even more modes because we found out that according to the sparse selector, a lot of modes that were still used are not actually useful. So we truncated even more modes than the original model. We're able to obtain, a lower error, but essentially not by a significant amount. It's essentially the same error, more or less, but our model is 3 times smaller. So with a 3 times smaller model, we're able to achieve basically a similar performance than the original model, simply with a simple idea of a sparse selector. So of course, we wanted to verify in 2D. So here we're trying to solve the Navier-Stokes equation. Again, we tried to compute a forward predictor, and this time instead of doing it for 1 time step, we do it iteratively for 10 time steps. Again, here we can see that a lot of modes are actually not used or not significant. Here we need also the negative frequencies to be truncated. So we show that we can sparsify it even more than in the original paper. And then finally, so we obtain a sort of similar error, and our model is about 30% smaller. And what's interesting is that if you look at the dynamics, so ground truth, the model, and then our own model, if you look at the borders between the different regions, you can see that there's a much sharper border compared to the ones in the original paper, which are more smooth. And so this sharpness kind of reflects the sparsity of our method. So because we use a very sparse number of frequencies, in the spatial domain, it's going to reflect in very sharp edges. So in this case, we indeed performed a sparsification of the original solution for the PDE. So this concludes my presentation. So we show that there's an implicit biases in CNN. So this allows us to design models that target specific bandwidths. Thanks to this implicit bias, we're able to perform a semblance of system identification in an unsupervised manner for different structures. And then from this project, we learned new techniques that can be applied for sort of a low-hanging fruit optimization of existing state-of-the-art methods for PDEs. Yeah, it concludes my presentation. I look forward to your questions.
Thank you, Kiran. Do we have questions for Kiran? Here or online?
Yeah, I got a question. Thanks, Kiran, for the nice presentation. Just for the last part about with the FNO, I find that pretty interesting what you showed. Did I understand correctly that? Can you just go back a couple slides where you show the
sort of the idea, I guess?
Yeah, the idea. So you're not actually, because with FNO, right, you can choose the number of frequencies, or like when you do the FFT, you can cut or keep some frequencies, right? Are you just using the same amount that they're doing with like in the original paper?
No, it's I kind of went over that, but here I use the full FFT during the training.
Yeah.
And then I let the sparse selector remove the frequencies. However, once we remove the frequencies, we obtain even less than when you just cut. Yeah, essentially.
Okay.
Yeah. That's why I plot this many frequencies. So this is because this is the original vector with a full FFT. That's why the vector is so long. But actually, you remove like 90%, 95% of the frequencies from the original FFT.
Yeah, okay, thanks.
Do we have any other question for Kiran? I guess if not, since we are also a bit tight with time, we can give the floor to Salma, that she's visiting us this. How long are you visiting for?
I'm here since mid of April.
Okay, you're unpaid when?
Mid of August.
Okay. I can give you my laptop.
So I can share.
You can share from there? Okay. Then it's fine.
Okay, so good morning everyone. So today I'm going to present you my master project that I'm leading with the Postdoc during this internship for a 4-month period. And now I'm going to present you what I did till now. So I will do a presentation of my mid-internship. The theme is about structural dynamics and augmented reality, and the subject is the visualization of a model analysis result by augmented reality. So first I will introduce you the core of the project, the goals, the objectives. Then I will talk about the theory that I had to acquire during the first few weeks. Then I will show you the chosen frame that I'm studying. Then I will talk about the numerical phase to get familiar with digital tools. So it concerns numerical implementation, then the start community, and finally I will talk about the further steps. So first, it's very basic, but before tackling the core of the project, it's necessary to understand what this model analysis and what this consists of. So it's a famous tool in structural engineering to solve the equation of motion by decomposing the system into different natural modes. And then we have the results of the displacements that were solved by model analysis. However, we have abstract results because of the vectorial expression. So we tend to visualize them in a more intuitive manner in a new perspective. So that's why we want to translate the results of model analysis into an immersive and visual experience via augmented reality to promote a more intuitive understanding of the structure's dynamic behavior. So this is the project objectives consists on, for my project, which is inspired of a previous project but with some improvements. This year it will be developing an automated digital model that allows more physically realistic visualization of model analysis results via augmented reality. So quickly, I will just talk about the theory. We all know the theory behind the dynamic structure. As I'm a master's student, so it just was quite new for me. So I had to go through some materials like the lecture plans, the courses at the ETH, the dynamics book of Chopra, and so I learned how. So it's from the real basic, like how to solve an equation motion under different excitation or an vibration situation, to understanding the multi degrees of freedom system and then model analysis theory and also numerical implementation behind it. So it's for deepening theoretical knowledge before going through the core of the project. And then this is the chosen frame. So it's a 4-story building. I chose this building. It's not simple, it's not simple, it's not that complex, but I think it's sufficient to understand and visualize the application of model analysis. But I could do it on a 2-story building. So for the numerical space, it's important to acquire some experience with mastering digital tools. In my case, I just implemented numerical methods on Python first because it's a simple way it's a quicker and simple way to modelize our first results. So first, for the numerical implementation, I proceeded to a comparison between different numerical analysis methods. But for this part, it will be just on a simple case like 2 degrees of freedom system. So I had to compare different analysis methods like numeric method, range Kutafor, and central difference method, and compare them with the analytical solution. So the objective is just to consolidate the knowledge of dynamic structures and to visualize the time history and to conclude that numeric method is the best compromise between precision and stability because it's an unconditional stable method under these parameters. So we have to enter specific parameters for the numeric method, so it is in conditional stable. These parameters are featuring the stability and precision of our numeric method. And then there is another part of this numerical implementation phase. It concerns the comparison between the numeric method, because it was the most efficient method that we compared for, and to compare it with model analysis method. But this time it's on the chosen structure. So here is the results of the time history of both numeric and model analysis methods for each degree of freedom. And as the model analysis is a very accurate method and a reference method for in terms of accuracy, it just confirms that numeric and model analysis can modelize best the time history of our displacement response. And this is just a figure that shows the implementation of the damping matrix with via the Rayleigh solution. So here we have just a simple implementation of the stiffness matrix, but we'll see that it can be improved to take into account the whole complexity of our structure, and it will be with the direct stiffness method. Yeah, so the direct stiffness method is also a tool used in civil engineering, in structural engineering, to model complex systems via finite elements. So the principle is to build local matrices and then assemble them in a global coordinate system and apply boundary conditions. So this method takes more into account the complexity of our four-story building, because we will have more degrees of freedom to take into consideration. We will have 3 degrees of freedom per node, compared to the previous implementation, which was very simple because it's just defining the system as a discrete system of punctual masses per story. So yeah, so here we have the first script that I had to go through a direct stiffness method that implements model analysis for our structure. So I had to change it, to adapt it, to have the result, to get the result of my mode shapes for my structure. So yeah, it solves the eigenvalue problem, it applies boundary condition, and it reduces the matrices, so it can solve the eigenvalue problem with the unblocked degrees of freedom. Because here we have the 2 first nodes are blocked, so we have 6 degrees of freedom that are blocked. So here we have the example of our mode shape at our second mode shape at 5.25 hertz. So it's the visualization of the second node at 5.25 hertz with fixed base nodes. And here the same script displays the natural frequencies of our structure. So here we can notice that we have so many nodes of the structure for only four-story building with the direct stiffness method. So, and now this is the core of the project. Is we start the part where we want to visualize the results of model analysis in immersive environments. So first we have to go through Unity, because it's a software that is linked to augmented reality devices. So first I had to get familiar with get familiar with Unity to understand the functionalities and how to code with C#, because it will just code all the interaction of the game objects in the software. So my first task was just coding a little game, a little platformer game that is moving a cube from left to right by avoiding some obstacles based on what Kostas gave me as tutorials. So it can be a bit challenging to get familiar with C# because I've never coded in this language, but now it's okay, so I'm fine with it. And yeah, so for the further steps, as I said previously with the direct stiffness method, I will just go back to the direct stiffness method, the visualization of our mode shape. We can see that the nodes are implemented manually because we do not have enough curvature of the displacements. So our goals is to implement as many nodes as we want per beam or per column. And the difference with the project that was led last year, where the nodes were implemented manually, is to create an automatic process to generate as much nodes as we want per beam or per column. So we will have a more accurate presentation of the deformation. So yeah, so this is the step that is left, is to generate automatically the nodes of our structure. And then it will be developing an augmented reality application with the MetaQuest Pros, the recent opposite receipt that Eleni gave me last week. It will be developed by using the mixed reality toolkit material. And then also in Unity, I had to go through the last year project to visualize the mode shapes of a beam. So it was a beam, but now our structure is a 4-story building. So I had to go through the last year project to visualize the beam, the deformation in the Unity scene. I also had to go through the scripts, to change some scripts so I can visualize all the modes and to understand which scripts are, what are the roles of each script to read the displacements, because they are stocked in shape files. So yeah, the future also a further step to be importing these data files to Unity, which contains our model analysis results. So thank you.
Thank you so much. Do we have questions for Salma?
Maybe a small note on my side that we're very happy to offer opportunities such as this one for Salma for students who do internships, which means at an earlier stage of their career. And so as part of the experience, it would be great if the students can interact also with the further group members. Of course, Salma interacts with the direct co-supervisor, who's Kostas Vlachas. But she's using a device and an instrument that many of you could use, which is this sort of augmented reality system, which requires coding on Unity. So there's a lot of things you could actually gain from exchanging with Salma, and then she could gain from you. So I want to encourage you to exchange if you have not already.
Sure. I would just like, I didn't understand, like you were saying in the beginning that you were doing some comparisons with different numerical schemes.
Yeah, it's just it's not really linked to the project.
Yes.
But it's during the phase where I had to deepen my theoretical knowledge of structural dynamics.
Okay, then we can discuss a bit, because I noticed a small confusion between model analysis and Geomatic method, because those are different things. It's not.
There are all different methods to solve the equation of motion.
Numeric is a numerical method, while model analysis is an approach that we use to extract the model properties of the system, but we can discuss that offline. I don't know if there is any question for Salma on her project.
I have a
Yes, go
question.
ahead.
I'm curious with the software Unity. I'm not quite sure how it works. Can you you import a model in, or you can create a frame in the Unity and
Yeah, I
apply
can create a
force?
frame like in Unity. I can create game objects, and then I can from the game objects I have the possibility to edit scripts, so it directly goes to the Visual Studio Code where I can code what I want.
So you can apply force, for example, on the frame in the Unity. Is that possible?
I did not for Unity. What I can do is to import some data files
I see.
and implement a score script. And in the score script, in Visual Studio Code, you can code the code. Your script will go directly to the data file that stocks all the displacement.
Okay, I see. Thank you.
Let me just
Any
say that Unity has a physics module. We are just not using it. So if you would like to have the physics resolved by Unity, it is possible. We just do every computation in Python and then do the model assembly and visualization in Unity. But if you would like, there are the physics modules that we can incorporate in Unity as well.
Yeah, I see. Thank you.
Any other question for Salma? If not, I guess we can also close here because we're 5 minutes over time, but I hope there is nobody waiting for the room. Yes, that's it. Thank you all for joining and see you next time, next group meeting. I think it's in July, right, Eleni?
That's correct, and thank you, Hara, for the moderation. It's July. Let me just make sure to give you the date. July 18th should be the next date, same time.
Yes, July 18th. I see we have no speakers yet.
Actually, it should be that Marcus and Wei will be presenting. So I'll make sure to fill out their names if they haven't yet. Okay.
Yeah, I can give one next time.
Okay, great. Wei, I will enter you in the list then.
Sure.
Okay. Bye, everybody.
Bye, bye-bye.
Bye. Bye.